Hello everyone, welcome back to my channel. You are learning with Dr. Shobha Nikam. In this video, I'll talk about implementation of AOI circuit using only NAND gates. Here, AOI stands for circuit using AND gates, and O stands for OR, and I stands for inverter. When we implement any circuit using AND, OR and inverter, we need to take those many ICs. Instead of that, we can implement entire circuit using only NAND gates, so that only NAND gate IC is sufficient. And this saves space on the board. And that is why it is always better to implement our circuit using universal gates, either using only NAND gates or using only NOR gates. So in this video, I'll tell you how to implement any circuit using NAND. So when we implement circuit using NAND gate, there are two ways. First method is, I will tell you equivalent circuit for AND gate, OR gate and inverter. NAND based equivalent circuit for these three gates. And you can simply replace your AND, OR and inverters using those equivalent circuits. And second method is where we connect bubble at the output of NAND gate and bubble at the input of OR gate, and then we place inverter. So I'll tell you both methods in details. First, I'll take one example. So let's take simple example. Y is equals to AB plus C bar. I have taken this example because it has AND gate, OR gate and inverter also. So first method is where I will tell you equivalent circuits for these gates. So first gate is inverter or NOT gate. For NOT gate, there is one input and one output. So input is A and output is A bar. So we can implement this circuit using one NAND gate. So see, you need to remember one table first. You have three gates, NOT or inverter and OR gate. And you need to implement them using NAND gate. So how many NAND gates are needed? So I need one NAND gate to implement, and I need two NAND gates, and to implement OR gate I need three NAND gates. This sequence you need to remember: NOT, and OR. So here, for implementation of inverter, truth table of NAND gate, it has two inputs, one output. I have considered two input NAND, 0 0 0 1, 1 0 and 1 1. NAND is what? Exactly opposite to AND. So in AND, when both inputs are 1, then only output is 1, otherwise output is 0. And here in NAND, otherwise output is 1, and when both inputs are 1, then only output is 0. So here I can implement this inverter using one NAND gate, and what I will do, I will simply short both inputs. So A, and here Y is equals to A bar. See how it works. When both inputs are 0, if A is equals to 0, both inputs are 0, then output is 1. So this condition is satisfied. When both inputs are 1, here A is 1, then both inputs are 1, so output is 0. So in this way we can implement NOT gate. Next is AND gate. AND is what? Inverted NAND. So AND gate is, this is diagram AB, and output Y is equals to A into B. I'll take double bar. If I'll take double bar of anything, it remains same. A, B, double bar. So here, how I'll implement it? I will simply, how many gates are needed? 2. I'll take one NAND gate. Inputs are AB. What I'll get at the output? I'll get AB bar. But what I want is AB. So I will simply connect one inverter here. And here I'll get double bar of AB, double bar. And this is nothing but AB. So by using these two NAND gates, I can implement my AND gate. Next is OR. Symbol of OR gate. Inputs are A, B. Output Y is equals to A plus B. I'll apply De Morgan's theorem here. I'll take double bar first. A, B, double bar. So this become becomes A bar into B bar, and 1 bar will remain as it is. So here I can implement this circuit using using NAND gates. This is what I want, A bar. So for this A bar, I will use one inverter by shorting both inputs. For B bar, I will use another inverter. But I am implementing this inverter using NAND gate. So this is my A, this is my B. Here I'll get A bar, here I'll get B bar. This is A bar, B bar, and there is NAND operation between them. And here I will get A bar into another input B bar and their whole bar, which is same as A plus B. So in this way we can convert our OR gate into NAND gate. So now you know equivalent circuits for NOT and OR. Now you just need to implement this circuit. In first method, we will simply replace these gates with NAND gates. So AB is multiplication, A, and other is B. So for AB, I will use one NAND gate and inverter at the output of that NAND gate. So here I will get AB. Here I'll get AB. Next is AB. I need C bar. C bar. For this C bar, I will take one inverter using NAND gates. So here I will get C bar, and then there is OR operation. There is OR operation, and for OR operation we need two inverters at the input side and then one NAND gate. So here for this input I will use one inverter. For this input I will use one inverter and then NAND gate at the output. So we can say NAND is equivalent to bubbled OR gate. See, here we have two inverters in series. So see here, you can see here we have two inverters in series. Here also we have two inverters in series. So when we have two inverters in series, they'll cancel. Because if I have A here, then I'll get A bar here, and here again I'll get A. So value at this point and at this point it's same. So no need to use two inverters. So equivalent circuit will become NAND, cancel, cancel. Here also we have two inverters in series. So cancel, cancel. So this is A, B, and I have C, and they'll come to input of NAND gate directly. So we can implement this circuit using this circuit directly. So here output Y is equals to, this is what? Here we'll get AB bar. So here what we have is AB bar into C and then whole bar. So if I'll apply De Morgan's theorem here, this will become AB double bar plus C bar. So this is nothing but AB plus C bar. So of course our implementation is correct only. Now let's understand the second method. In most of the books you will find this method. So in this method, first step is step 1. Okay, I'll write steps first to save the time, and then I'll explain. So the steps are: add bubble at the output of AND gate and input of OR gate. Then place inverter near bubble, that is before OR gate and after AND gate. If two inverters are there in series, then remove both of them, just like we replaced in the first method. Replace gates with NAND gates. So let's start with this implementation. AB plus C bar. So AB means AND gate, plus C bar. So C bar is inverter, and here I'll have one OR gate. This is my AOI circuit, and or inverter circuit. So here I'll get my output Y. What I have is AB plus C bar. First step is add bubble at the output of AND gate. So I will draw this circuit again and I'll simply add bubble at the output of AND gate. So here I'll add bubble. Inverter will remain as it is. We have not to do anything with inverter. And we need to add bubbles at the input of OR gate. Bubble, bubble. And here is my output Y. Next step is place inverter near bubbles, because here value changes. Here what was our output? AB. What we are getting? AB bar, but we don't want functionality to change. So put inverters near bubbles. In this NAND gate, I'll put inverter here. This is A, B, and this is C. Before these two bubbles, I need to add two inverters. So I'll add one inverter here, and before the other input again I'll add one inverter. And this OR gate will remain as it is, bubbled OR gate. And here is output Y. Next step is, if inverters are there in series, replace them. So these two are in series, no need to connect them. These two are also in series, no need to connect them. Here circuit will become first NAND gate as it is, A, B, here C, and bubbled OR is nothing but NAND. And here I'll get output Y. So this is the equivalent circuit of this AB plus C bar using only NAND gates. So here you can see, if I'll implement this circuit on my board, I need one AND gate 7408, 7432, 7404. But here I can implement using only NAND gate 7400 IC. That's it. So it saves the space on the board. So by using these two methods, you can implement any circuit, any AND or inverter circuit using only NAND gate. I can feel second method is very easy. You just need to write these steps, step 1 to step 4, and then you just need to implement your circuitry. I hope this will be useful to you in your exam. Thank you so much for watching. Don't forget to subscribe, share this video with your friends, and don't forget to like. Thank you so much for watching.